So in the previous example, we had shown that the limit for this particular function did in fact exist, and it was 0. We considered a path, I have labeled here path 1, coming along the line y equals x. And we had attempted this path 2, which was a generic path, r cosine theta, r sine theta. Along the generic path, we saw that using that replacement of x to be r cosine theta and y to be r sine theta, we were able to establish that through L'Hopital's rule to show that the limit is in fact always 0. Let's look at this next example. And we're going to try a couple of paths, and in this particular case, we're going to see that the limit does not exist. So we're going to try two paths. We're going to come along the positive x-axis as our first path, and then along the line y equals x as our second path. Okay, so along the x-axis, we're going to allow x to be t, to be our parameter, and y to be 0. And as I allow myself to move along points along this path, xy points, my xy coordinate pairs, as they approach 0, 0, then that forces the t parameter to also approach 0. And it's going to approach 0 from above because I'm coming along the positive x-axis, and so those x values are positive, but they are getting closer to 0. And since we set our parameter to be t equal to x, then that same behavior is going to occur for the t parameter. At this point, once we have made this parameterization and noted that this would cause t to equal 0, then we can go ahead and plug this information into our limit. And so we'd have the limit, instead of xy going to 0, 0, we'll have t going to 0 from above. I replace x with t, y with 0. So when I do that, my numerator becomes 0 over t squared. But as I simplify 0 over t squared, as t approaches 0, I don't have an indeterminate form. I can actually simplify that, and I actually do get 0. And so the limit as t approaches 0 of 0 is equal to 0. Okay? So that's fairly straightforward. Now, it's the second path where we have y equals to x. Well, if y equals to x, then they should both equal, in theory, our parameter. So if y equals x, and we choose x to be our parameter t, then what's going to happen is, and if I look at my line up here, as I move along that path, my x and y coordinates are getting closer and closer to 0 from above. So notice I have, as xy approaches 0 from above, 0 from above, because both x and y are approaching 0 from above, then that will force my parameter, which is also x and y, to be going towards 0 from above as well. So what this does is this allows me to rewrite my limit. So instead of, again, having the limit as xy approaches 0, 0, I am going to have my parameter t. So limit as t approaches 0 from above. And I replace x with t and y with t. So I have negative xy over x squared plus y squared. So doing a little bit of simplification, keeping my limit notation, I'll have negative t squared over 2t squared. And then I'll have the limit as t approaches 0 from above. If I simplify that, the t squareds become 1. So I get a negative 1/2. So as I let t go to 0 from above, of negative 1/2, I end up with negative 1/2. So notice along path 1, our limit was 0. along path 2, our limit was -1/2. And as we discussed, it has to have the same limit along any path. Well, since we found two paths that produce different limits, then we say that the limit does not exist because the limit has two different values along two different paths going towards the origin. Okay, so this leads us into the idea of continuity. So you saw continuity back in Calc 1, and continuous functions have a very nice property, and that property is that if I have a function f that's continuous and I'm interested in what the limit is as xy approaches ab, because this function is continuous, I can simply evaluate this function f of x and y at a and b, or the x and y that we're interested in. So back in Calc 1, you probably saw the three-part definition for continuity. We're not going to necessarily worry about that in Calc 3. We're going to assume that we understand what continuous functions are and how they behave. Okay, so continuous functions are continuous on their domain. So, for example, the square root function is continuous on its domain. It's continuous for all positive values. So we're going to look at a couple of examples. Okay, so some of the properties that we have for continuous functions is if I add two continuous functions, I get another continuous function on its domain. If I subtract two continuous functions, I have another continuous function on its domain. Same is true for products and for quotients. They're all continuous on their domains. And keep in mind that when we're doing quotients of continuous functions, that we do have to be cautious of where the denominator has the potential to be 0. Now, there are a number of familiar functions, continuous functions you're familiar with. So things like polynomials, trigonometric functions, rational functions, all of those are continuous functions that you've worked with for quite a while. So what's really the only thing new here is instead of these being functions of a single variable, they are now functions of 2 or 3 variables. So let's go ahead and take a look at a couple of examples. So here's our first example. Discuss and sketch the region for which each function is continuous. And so my f of x and y here, x cubed times y plus 2yx plus 4, that's a polynomial. All of the variables are raised to integer powers, positive integer values in fact, and that's what makes it a polynomial. And because it's a polynomial, we know that it's continuous over all real numbers. And since we have both x and y, it's actually all of R2. So I can evaluate this function for any point in the xy plane. So I would say that it's continuous for all points in the xy plane. You could write it something like what I have here. Okay, or you could just say for R2 or for the xy plane. That would be fine as well. And if I'm going to sketch the region or the domain is in the xy plane. So here's my xy plane. I have that this function is continuous over the entirety of it. So basically I have shaded the entire xy plane. And here we have a second example. Now notice that this particular function has a square root in it. So it's a root function. And we know that root functions are continuous on their domain. That means that what is under the radical or the radicand has to be greater than or equal to 0. Okay, so that means x minus y in this particular instance is my radicand, so it must be greater than or equal to 0. Well, if I add y to both sides of that inequality, I have x has to be bigger than or equal to y. Or I could rewrite that y has to be less than or equal to x. So if I was to describe the region on which this function is continuous, I would probably say something like all of the points x, y in the R2 such that y is less than or equal to x. You don't necessarily have to use that set notation. That's the mathematical notation that's more precise. You could simply say that y is less than or equal to x. Now as I go to graph this, we've got the xy plane here. Notice I graphed my line y equals x, and I shaded the region underneath that line because y has to be less than or equal to x. So here's our last example, and I tried to go a little crazy on this one to combine both rational and root functions. So when I look at this, I see something that looks like a fraction, but in my denominator I have a square root. So I have to really balance two things. First of all, my denominator cannot be 0. So this square root of x squared plus z squared minus 1, that cannot be 0. Now, on top of that not being 0, I also need that's what my radicand is, this x squared plus z squared minus 1, that also has to be greater than or equal to 0. Well, if I balance both of those, if I take them both into consideration, we see, okay, well, my x squared plus z squared minus 1 can't be 0 because it's in the denominator. So I have to then combine those two pieces of information and come to the realization that x squared plus z squared minus 1 must be greater than 0. Okay, so that is my domain for this particular function. So I would say the set of all x, y, and z, I'm missing in R3, but the set of all x, y, and z such that x squared plus z squared minus 1 is greater than 0. Now, I have to graph this. Notice that in this particular function, I have three independent variables, x, y, and z. So the domain is in R3. So when I go to graph this region for which it's continuous, it's going to be in all of R3. So what I did is I started by graphing x squared plus z squared equals 1. That's this circle in the xz plane. Noting that y is absent from that inequality, meaning y can be any real number. Basically, I have a cylinder, and this cylinder of radius 1 with a center along the y-axis. Now, this x squared plus z squared has to be bigger than 1, so I actually need the outside of that cylinder. That is what my domain would be. So since this picture is a little hard to interpret, and whenever a picture might be a little hard to interpret, and we can describe it verbally a little more clearly, we should always do that. So notice I have here outside of cylinder centered along the y-axis with a radius of 1. That is what I'm trying to portray in that picture, and that would be the region on which this function f of x, y, and z is actually continuous.